Hey everyone, so in continuation of my GAN series, today in this video I will implement conditional GAN from scratch with PyTorch. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. One more thing, that over the next month I will do many GAN or Generative Adversarial Network implementation from scratch with PyTorch. So do subscribe, because you hitting the subscribe button is what keeps me motivated to do this. Let's start. So first, what is a regular GAN architecture? This is a representation. You pass a noise vector to the generator and that produce a fake image represented by G of Z, and that fake image is transferred to discriminator as input, and the discriminator also gets the real images to it, and then it produces real or fake 0 1. So the discriminator is a binary classifier that produces real or fake. So now here in this regular architecture of GAN, suppose you train a GAN on handwritten digit and you normally cannot control what specific images the generator will produce. In other words, there is no way you can request a particular digit from the generator. So a regular GAN is trained in a completely unsupervised and unconditional fashion, meaning that no labels involved in the training process. So, though the GAN model is capable of generating new realistic samples for a particular dataset, we have zero control over the type of images that are generated. But what if instead of a random image generation, I want to generate a particular image? Say, in the case of MNIST, I want to generate only 7. Can I do it in regular GAN? No, we don't have control on that, because we are not feeding the generator or the discriminator model any label information. And this is where CGAN or conditional GAN comes in, as we can add an additional input layer of one hot encoded image labels. This additional layer guides the generator in terms of which image to produce. So in this slide we see the architecture of conditional GAN, the generator and the discriminator. So looking at the generator architecture, this uses the noise vector Z and the label Y to synthesize a fake example. So this here is the output after Z and Y goes to the generator, and this notation here is, you can read it as X given the condition Y, and Y, what is the condition Y? This is that label vector. So the generator is parameterized to learn and produce realistic samples for each label in the training dataset. And looking at the discriminator architecture at the bottom right corner here, it receives both the real images and real labels, and also the fake images with the corresponding labels that was used to generate them. And remember, here discriminator always is working with this pair, that is, it's always looking at X and Y together, both the real X with the corresponding labels and also the fake images with the corresponding Y. So on the real examples and label pairs, that is XY, the discriminator learns how to recognize real data and how to recognize matching pairs. On the generator produced image set, that is this X hat with corresponding layer, the discriminator learns to recognize fake images and fake label pairs, thereby learning to tell them apart from the real ones. And finally, the discriminator outputs a single probability indicating its conviction that the input is a real matching pair. So overall, the discriminator's goal is to learn to reject all the fake examples and all examples that fail to match their label, while accepting all real example label pairs. And one thing to note here, that for each fake example, the same label Y is passed to both the generator and also the discriminator. And here are some important rules that the discriminator of a CGAN should follow. let's say I have passed to the discriminator a handwritten numerical image 3, and with that also the label 4. So basically I have passed to the discriminator an image 3 with label 4. So in this case, the CGAN discriminator should learn to reject this pair regardless of whether the example, that is this handwritten numerical image 3, is real or fake. That's because the image and the label does not match. That is, the image is 3 and the label is 4. So this is an obvious case for the discriminator should reject this image even if this image is real. And then the next rule is that the discriminator should also reject all image label pairs in which the image is fake, even if the label matches the image. That is, if the discriminator is passed the same image and label, that is image 3 and label 3, but it should get rejected if the image is fake. And with that introduction on the architecture of conditional GAN, let's start the actual implementation. So I am back in my VS Code, and the main point is that overall project structure for CGAN is very similar to DC GAN or a normal GAN. Only difference is that I have to include the labels of my input image as a vector to the generator and also to the discriminator. And what that means is that, for example, let's say mnist is my data set. So in mnist, I have the y vector, that is the target labels, is a number from 0 to 9. So what I do is I create a label vector y by creating a uniform distribution to generate a number from 0 to 9. Then I encode this value into a one hot vector, and that means for example the number 3 will be represented as this 0 0 0 then 1. This represents a number 3 in one hot encoded vector, and also the rest are all zeros. Similarly, if the number was 4, then this place will contain 0 and the next place will be 1. And I feed these one hot encoded vector and the noise z to the generator to create an image that resembles number 3. That's the whole job of generator. And for the discriminator, I add the supposed label of 3 as one hot vector along with the image input. And for the image input, discriminator will take, just as usual, both fake images and also the real images, and ultimately decides between them. So now coming back to my project implementation, just like my other videos implementing the other GANs, I have 3 files. The first one is the actual network implementation of CGAN, which is I'm calling ConditionalGAN.py. I have a train file, and also I have a small util files that will have couple of utilities method. So starting with the conditional GAN, I will rather go over these structure rather quickly because it's these generator and discriminator is not too different from a normal DC GAN in here. So the key thing in generator is that I have a sequential block defined under my this method, generator block. So that method will actually implement a network of a conf transpose 2D, and that will be repeated in my generator network. So this generator block is like a utility method inside my generator class that will be invoked repeatedly to build the generator block, and this is the exact kind of workflow that I have used in my other GAN implementation in the other videos. So if you have watched them, you will be familiar with this. So what this generator block is taking is input channel, which is how many channels the input feature representation has, then output channel, which represents how many channels the output feature representation should have, and kernel size strides are obvious, and final layer is just a boolean, it will take true or false. So first, if it is not a final layer, then I am just doing these 3 things, that is a conf transpose 2D, a batch norm 2D, and a ReLU. And if it's a final layer, then I do not need the ReLU and batch norm. Instead, I have a single conf transpose 2D and tanh. And then I am invoking these generator block in here to build my this .gen sequential network. And remember, this generator block is implementing conf transpose 2D, so that means I have to downsample while moving forward through the network, and that's what I'm doing here. So first, while I'm implementing generator block, it's taking the input dim coming from the argument, which is by default will take 10 because this is mnist. And then the hidden dim, that is output channels of my generator block, that starts with 4, that is hidden dim multiplied by 4. Then in the next layer, hidden dim multiplied by 2, it's get downsampled by half. And then in the third, hidden dim multiplied only hidden dim, it's again halved again here because the downsampling is going on. And then in the last block, that is a final layer, my second argument to this generator block, that is the output channel, will become my image channel. And because in this case, for this video I'll be using mnist dataset, this needs to be 1 because it's a grayscale dataset, and that's what I am defining my image channel as well in the argument. And kernel size remains 4 across the network. And obviously in the final layer you will place final layer equal to true. And then the forward function of my generator class is just this, super simple. It just the forward function takes a noise vector and then reshapes this noise vector with the view method to be compatible with the 4-dimensional tensor that PyTorch expects. So the first one is batch size, then channel number, height and width. And for defining my height and width, I'm creating this new two dummy dimension here with 1 and 1, so that these x becomes a 4-dimensional tensor that can be feeded into my generator network, that is at the very starting layer over here. And the next line of this forward function is just doing that. It's feeding these noise vector after reshaping to my generator network, and the output of this generator network will be the return value from my forward function. So that completes my generator network. And then I have a very small utility method here just to create a noise vector. And this is again the same kind of method I have used in my other GAN videos. It just creates a simple noise vector with torch.randn, and as an input it takes number of samples and input dim. So this will create a tensor with the first dimension of that will be n samples and input dim. And the usage of this function is mainly done in my train.py file, where within my generator training I'm creating this fake noise, you can see here. So fake noise is create noise vector, to that I'm passing the current batch size and zdim, and zdim is my hyperparameter that will be defined at the very top to be, let's see, yeah, zdim is 64. So anyway, that method will just create the very first vector to be fed into the generator. And all right, now let's come to my discriminator network. Here again I have this little utility function, discriminator block, that will just create a single block, and then this method will be invoked again and again to create my network, that is a discriminator network. And what this function here is doing is, again, if the final layer, if this is not a final layer, it will apply conf2d, batch norm 2d and leaky relu, and otherwise that for the final discriminator layer it will just implement a single conf2d. Otherwise the arguments remains just the same, just like what we did in generator. And then for the implementation of this discriminator block method, here is my network. So it just invoking these discriminator block method 3 times. This is the first layer, and remember here it's a conf2d. That means I have to upsample while I am moving forward through the network, and that's what I'm doing in the invocation here. That is for the first layer, my hidden dim is output channel to my discriminator block function. Then in the next layer I'm multiplying hidden dim by 2 and that's my output channels for the next layer. and then the final layer, my output channel needs to be 1, and that's why you are seeing here. And why 1? Because this is MNIST, where the channel number is 1. And then let's quickly see what are the methods that utils file has. So the first one is again that I have used in many other GAN, that is this method just plots the images in matplotlib given a tensor. And only key thing to remember in this function is that you have to convert the tensor shape from a PyTorch tensor to something which is acceptable to matplotlib, and that's what I'm doing in here. That is once I get the tensor, then first I am detaching it, that is removing the gradient tree from the tensor, and then make use of make grid to make a grid of the tensor. And then I am passing this image grid to my plt.imshow, that is to matplotlib, but inside the imshow argument I am converting the shape with a permute from to 1 to 0. That means the reason I'm doing this, I have put that in detail in the comment, that the image in a tensor in PyTorch is acceptable in the form of channel number, height, width, whereas in matplotlib the expected image shape should be height, width, and then channel number. And that's why I have to convert these. So here in the permute, this one actually represent my height, which is coming from PyTorch, 2 represent my width, and 0 represent channel, because in PyTorch the 0 that is the first index, that is the first dimension, represent the channel, but it comes as a last dimension in matplotlib, and that's why I'm using this permute. Okay, let's move on. Then I have these wait init method. Again, this method I have used in my other GAN videos as well. It just creates the weights depending on what kind of conf layer it is. That is, if my current object is an instance of conf2d or conf transpose 2d, then this is my weights, and I'm just defining the mean and variance here. And if my current layer is a batch norm 2d, then this is my weights, and also this is my bias. That's just initializes the weights. Now here I have couple of methods to deal with which is specifically about conditional GAN. That is, I have to given a label vector containing 1 2 3 4 5 6 7 8 9 0, I have to convert that to a one hot encoded vector, because that will be concatenated with my image to get a final vector that will be fed into the generator. So this little function, a single method, is just producing that one hot encoded version of my labels. It's very simple, just a single liner. That is f.1hot. So 1hot is coming from the module of PyTorch. And what is f? F is just my torch.nn.functional that has this 1hot encoded vector inbuilt. To that you just pass the label vector and also how many classes you want to have in this label. So because in my MNIST dataset is a number of classes is 10, so I'll be passing 10 as a num classes. And the way this one hot vector works is, I have put that in this comment. That is, if you pass, for example, 43210 as your labels, and then number of classes is you pass 6, then after doing f.1hot, your x vector, that is original was this tensor, that will be converted into this form. So you can see the first element of my original input tensor is 4, and here after the one hot encoded conversion, this 4 is this place, that is 0 1 2 3 4, because this 4 is represented by this number 1 here in the encoded version. Then the next element is 3, and so that will take the third place, the 3th index place in my output tensor of the one hot encoded vector. That is 0 0 1 2 3. This is the third place, 3 index. Similarly, let's say the last element, this one is 0, that means for the one hot encoded version it will take the 0th index, which is 1. So that's why you see 1 here. So this is pretty much how it works. So in my case, the original input will be 1 2 3 4 up to 10, and then the number of classes will be 10. And then I have these little method concat vectors. What it will do, it will just concatenate to float tensor and return me the combined concatenated vector. And why I need is this, because if I go back to the slide architecture of CGAN, so in the generator in CGAN, it doesn't only take the regular Z vector, that is a noise vector, it also takes a label vector. So that concat method of my architecture here, that is concat vector, will actually concatenate these Z noise vector and the label vector, and then pass the concatenated vector as an input to the generator. Just one more thing on this torch.cat usage, that to concatenate with torch.cat, where the list of tensors are concatenated across the specified dimension, requires two conditions to be satisfied. The first condition is that all tensors need to have the same number of dimensions, and all dimensions except the one that they are concatenated on need to have the same size. Let's quickly see an example, it will make more sense. Let's say I have my code like this. So I have T1 and T2, two tensors, both are three-dimensional. That is, both of them have same number of dimension. That means the first condition is satisfied, that all tensors need to have the same number of dimensions. Now the second condition is that all dimension except the one that they are concatenated on need to have the same size. That means say I am concatenating by the dimension of 2, that is this third dimension. Let's see if it runs and prints proper shape. Indeed, so they got concatenated, and because I was concatenating them by these number 2 index dimension, that means 3 and 3 got added. My output is 6 here. Now let's change this. Let's keep it as it is. Let's change this to 0. That is, now my second condition is no more satisfying. That is, the second condition, all dimension except the one that they are concatenated on need to have the same size. This is no more the case here, because here 32 and 30. Let's see if it runs. And I got an error as expected. Runtime error, sizes of tensor must match except in dimension 2. And why except? Because I am concatenating by this dimension. So let's revert it back to 32, and let's change this one because I'm concatenating by this dimension, and now these two dimensions are mismatched. They are not matching. Let's run it, and I got a properly combined concatenated tensor. That's because this is a dimension that I am concatenating them by. So that means I can have a mismatch in this dimension, and in that case output will have 3 plus 4, 7 as my output concatenated tensor dimension. So keeping these things in mind is very important while you are doing with large dimensional tensor, because making them compatible is extremely important in almost any deep learning projects that you will do. Anyway, coming back to my utils method, and the last util method I need is this calculate input dim. So this will just pretty much gives me the input dimension given my noise vector, the MNIST shape, and the number of classes. And zdim, that is a noise vector, is a hyperparameter. That is, the dimension of the noise vector is a hyperparameter that I will define in my train file to be I think 64. Yes, 64 is a dimension of zdim. And for MNIST shape, this is 1 by 28 by 28, and number of classes is 10 because MNIST has 10 different classes. So let's see what I'm doing in this method. So generator input dimension will be zdim plus n classes. And why is that so? Because if I go back to the architecture of generator, I have zdim plus the y vector, that is a target classes vector of my MNIST dataset to be combined to be fed into my generator. So that's what this line is, and then my discriminator image channel will be MNIST shape 0 plus number of classes. MNIST shape 0 will be 28 and n classes is 10. That's because the discriminator does not start with the noise vector, rather it starts with the image vector and the target classes vector, and the image vector could be either the real set of images or the fake set of images generated by the generator. So discriminator takes both these images in different parts of the training loop and outputs the probability of it being real or fake. And that's why the input to the discriminator will be the MNIST shape 0, that is 28, and number of classes. And this function just returns these generator input dimension and the discriminator input dimension. Now, why do I need, or where is the usage of this function? Is because inside the training loop, I will be using these concat vectors. Let's see the usage of this concat vector, then we will see why we need this separate function, calculate input dim. So if I go to my train file, the concat vector will be used inside my train. Yeah, so this is the kind of usage of concat vectors, that will take the fake noise and the one hot labels and concatenate them to be these vector noise and labels that will be fed to the generator to create the fake images. So why do I need this separate function again? That's because what we saw, the usage of concat vectors, that was inside the training loop, but outside the training loop, when I am generating or initializing my initial set of weights to initialize my optimizer, that's when I also need a vector to my generator object. That's why I need this function. Let's see the usage. So if I go to my train file again, no, sorry, I need only this calculate input dim, and I have single usage of that. Yeah, so from the calculate unit input dim, I am getting the generator input dim, and this generator input dim is passed to my generator class to create my Jane object. This is where I'm initializing a Jane object, because this Jane object I need to pass to my optimizer to initialize my optimizer, and then to create my first Jane object by applying the weight init method. So that's why I need an initial set of tensor to be to create my Jane object, and also the same I need to create my disk, that is the discriminator object, which will have as input image channel as discriminator image channel, that is the output of this calculate input dim. All right, I think with that I am done with the utils file. Now the last part, which is the train part, and again I'm just following the similar structure that I have followed in my other GAN videos, so the training is not too difficult. First I'm just creating all these hyperparameters, number of epochs 200, zdim 64, etc. MNIST shape, in this case I will be using MNIST dataset, that's why this is my shape, number of classes 10. All right, and batch size I'm keeping at 128, learning rate 0.002. So just initially I am creating this transform which will apply the very basic transforms to my MNIST dataset, and also I am making use of this data loader method to create my data loader which will feed the training loop batch by batch data from the MNIST. And then in these next few lines, what we just discussed, that is I am initializing my optimizer and also the initial Jane object and disk object by feeding the generator class and the discriminator class these initial tensor that is created from this calculate input dim that we just defined in the util function here. All right, so now my Jane and disk object is defined, my optimizer, Jane opt and disk opt is also defined. So now let's come down and here the actual training starts, that is for epoch in range. So and before that, I'm just defining few variables that I'll be making use of inside the training loop. That is current step, generator losses, discriminator losses. These two arrays pretty much will keep track of all the generator losses for different epochs. And then here starts the most important part, which is my training loop. And just following the normal workflow for all other GAN training, I will have two loops. The first one is for epoch outer loop, and the inside loop is for my where the actual training code will be executed. That is, it will start with each batch, and that's what this line is doing. That is, from my data loader, I will get each batch of data from the MNIST whole data set, and that will have the real images and also the labels vector. And then I am creating these, passing these real images to the device, which is I have defined to be CUDA, that is, it will use my GPU. And then the first variable, I'm creating these one hot labels by using this OHE vector from labels that we have defined in the utils file to encode the labels to be one hot encoded. And immediately after creating, when I'm printing this one hot labels vector, this will give me a size of 128 by 10. Why 128? Because that's my batch size. That's the number of sample in each batch, and 10 is my number of classes in my, that is a number of labels that I have in MNIST. But because in the next phase of my training, I have to convert this two-dimensional tensor of one hot vector into a four-dimensional tensor, because I will be applying concatenation with my images, and images are four-dimensional in PyTorch. That is batch size, channel number, height, width. That's why the first thing I need to do is convert these two-dimensional tensor of my one hot encoded labels to be a four-dimensional. That is what I need. Is I put that in detail in these comments here actually. That is, this 128 by 10 need to be converted to these four-dimensional tensor 128, 10, 28, 28, because this will be the shape of my images coming from the MNIST. So let's do that. So for doing that, the first thing I am doing, I will definitely give the link of this file in the description, so you can go through these comments in detail. So first thing I'm doing to convert, I am making use of this none keyword. So what this none keyword will do, it will add some dummy extra dimension to the original tensor. So one hot labels was my original tensor, that I am taking the first two dimension, and then I'm appending these two extra dimension. And then after adding this none keyword to add dimension, if I print these image one hot labels in this next line, what I will get is these new tensor, which has already now become a four-dimensional tensor. That is, we see 128, 10, 1, 1. So these two extra dimension we just added with this none and none keyword. But I need this 28 and 28. So now I will be making use of the repeat method of PyTorch that I'm doing in the next line here. That is, now image one hot labels dot repeat. I'm keeping the first two dimension as it is. That is, I do not need to repeat it. That is, they will be repeated just once, and that's why 1 and 1. Then this needs to become 28. That is the height and width of MNIST, 28 by 28. So that's what I'm doing here. MNIST shape 1, MNIST shape 2. And remember, our MNIST shape is 1, 28, 28. 1 is the number of channels, 28 and 28 are height and width. So with this repeat method, these two dimension will actually become repeated, and finally the shape that it will produce is this. That is, if I'm just printing these this final variable here in this line, and now my size has become 128, 10, 28, 28. Exactly what I want it to be, because now this is exactly this exactly matches the images coming from the batches, coming from the data loaders. with that, all my data preparation is ready and all my data is of correct shape. So start the discriminator training from here. So let's zoom out a little bit. Let's show you the overall structure. So all these lines are my discriminator training up to here. Then I will start my generator training that will go on up to here. Generator training is relatively easier in CGAN. So yeah, although the discriminator training is long, that's because I have put a lot of comments, and actually this is not that long really. And let's just start going through them. So as always, before starting the training, just like in other GAN, you have to clear out, you need a clean slate of gradients. That's why you apply 0 grad. That will zero out the accumulated discriminator gradients. Then create a fake noise with create noise vector. We define this in util, and to that you pass current batch size, which is 128, zdim is 64, and then device. Now I have fake noise, so I need to do these two steps. You can get the images from the generator. Steps 1, combine the noise vector and the one hot labels for the generator and generate the conditioned fake images. So I have to concatenate my fake noise with one hot labels with concat vectors that will give me the concatenated noise and labels that I'm passing to my generator, and then that will produce my fake images. Alright, so I got my fake images, and here's a little unit test. This is not important. I just made this to check that the length of them matches actually. That is a fake length of fake matches length of real. That is enough number of fake images has been produced. And what is my real? Remember, real is my coming from data loader. So when I'm looping through my data loader, these two things I'm getting, real images and the labels vector. So now that I have both the real images and fake images, I need to get the predictions from the discriminator. And for that, the steps are first create the input vector that will be passed to the discriminator. And what will be my input vector? So for the real image, for the fake images, I have to combine the fake images with image one hot labels, and for the real images, I have to combine the real images with image one hot labels. Remember, as we discussed in detail, that the discriminator and generator here cannot take only images. Both of this network here in conditional GAN takes images as well as the label vector, and that's what these image one hot labels. So we have to combine them and pass to the discriminator. So let's do that in the next line. That is, I'm combining the fake images with the image one hot labels with concat vectors. That will take fake and image one hot labels. Again, in the next line, I'm passing real and image one hot labels. So I get both fake image and labels vector and real image and labels vector. So I'm all ready to pass these two input vectors to my discriminator in the next line here, next two lines here indeed, so that I get the prediction from the discriminator. And that's what I'm doing in the next two lines. So here these two variables, that is these two outputs actually represent my prediction from the discriminator. And these two, just again little two unit test lines. This is not really important within the training loop, but I just made sure that I'm moving forward correctly and I do not later get into any problem. So I'm just checking the length of disk real prediction and the length of real is same, and also I'm making sure that the inputs are different. That is torch.any fake images and labels not equal to real images and labels. That is what it is supposed to be. So now that I have the actual images and also the prediction from the discriminator, I can calculate the discriminator loss on fake and reals. So these two lines are just doing that. That is calculating the loss, and I'm making use of this criterion, and our criterion was defined to be BCE, that is binary cross entropy loss with logistic. We can check that. Where did I define? Yeah, so criterion was defined nn.bce with logistic loss. All right, let's come back. Yeah. So these criterion just takes the prediction, and also for the fake, it calculates the loss between the discriminator fake prediction and all zeros vector, that is torch.zeros like and discriminator fake prediction, because these are fake images, so they all should actually be zero target, and that is their target value should be zero. That's what I mean. That's why I'm using torch.zeros like. And for the real, I am calculating the loss between the prediction and torch.ones like, because they are the real images, so they should all be ones. And finally get the average of discriminator loss, just dividing them by 2. Alright, with after the loss, just do the back propagation and updating the weights with dot backward and dot step method respectively. Very standard step here, nothing complex going on. And finally, because I have to plot all these losses at the end, so I need to keep track of these batch losses, and this line is just accumulating the batch losses in this vector, in this variable discriminator loss. Okay, so with that, discriminator training is done, and now I need to do the little generator training. This is relatively simpler. First step is, as usual, zero grad. Then again, I'm creating fake images and labels, this vector, by concatenating fake and image one hot labels. And now that my fake image and labels, this concatenated vector is ready, I can pass this as input to my discriminator to get the prediction from the discriminator. And then the next line does the generator loss. Only important point and the difference with the discriminator to note here is this part. That is, although the generator is creating fake images, but here I am using torch.ones like, because look at the difference with the discriminator. Here for the disk fake loss, I used torch.zeros like, because here I'm passing the fake the discriminator's prediction from the fake images, and because they're fake, they all should be zero target value. But in the generator training, I am passing those fake image prediction from the fake images and getting the prediction from discriminator, and then I'm comparing this predicted vector with torch.ones like, because here the generator wants to fool the discriminator. That is, although these are fake images, what generator is telling to the discriminator that they are real, and that's why I'm comparing with I'm bringing in torch.ones like. And after the loss calculation, just do the regular back propagation and weight updates with backward and step. And the last line of generator training is just to keep track of the generator losses in various batches by appending to this generator losses list, because ultimately at the end of the training loop, I will need these two variables to plot the graph. And yeah, that's where my generator training is pretty much over. The next part, let's zoom out a little bit. This part is just for logging and plotting, no complex things here, and exactly the same kind of code I used in my other GANs as well. That is what I'm very much doing. That is for each 50 step, this display step is a hyperparameter that's been defined at the very top to be 50. So at each 50 step, I am plotting the generator losses by taking the last 50 losses. That's what this slice notation is doing. That is list, then you pass minus x and slice, that will extract the last x items in the array. So from my generator losses, which has all my losses appended to it, I'm just taking the last 50 and taking a sum of them and plotting them, so and dividing by display step to get the mean generator losses, and then I am plotting that mean generator loss. And I'm doing the same thing with the discriminator as well. So this print statement will just print these two, mean generator loss and mean discriminator loss, and the actual plotting code is these lines. So we made use of this plot image from tensor method that we defined in utils file, and I'm plotting both the fake and real one after another. so that we can actually check the improvement of the fake images when the epochs moves forward. And then also in the last part of this plotting, it's very simple code. I'm just doing the plt.plot to plot a graph of my generator loss and the discriminator loss for across the epochs. And with that, all my code architecture implementation is over and I'm ready to run the entire project. And to run the entire project, all I need to do is execute this train.py file, because this file is bringing in all the other methods from the other two files with these two imports. So I am going to go to my Google Colab. And in Google Colab, all you need to do is to upload these three files in your current session storage of Colab. That is, my file names are ConditionalGAN, train.py and utils.py. You can just click here in this upload icon. That will bring the prompt, and just select your files and it will be uploaded. Then I'm connecting my Google Drive. NVIDIA SMI will just check what kind of GPU I got. You have to actually change the runtime type to be GPU. So I got a Tesla K80 GPU with 12 GB of VRAM, and run the ls command to check all the files that you uploaded is recognized. And then final training is just this simple command, python train.py, and that will start your training. And after the very first epoch was done, this is the kind of result I got. So on the top here you see the fake images produced by generator, and that's almost just noise after the first epoch. And then this is my real images from MNIST, and this is the loss plot, and we can see that there is almost no convergence of the losses, and that's because it's just one epoch. And then after 4 or 5 epochs, I can see that the images are starting to be formed. That is, these top images are my fake produced by generator, and here I can kind of recognize some of the images. And also the loss plot looks better. They are starting to converge. And then finally, almost after 30-40 epochs, I can see the fake images looks almost like real, and that's like after I think after 50 epochs, 50 or 60. So yeah, it looks much better, and also the loss plot is really looking better. The convergence of them looks very nice. That pretty much wraps up this video, and the GitHub link is in the description. And finally, over the next couple of months, I will do many popular GAN or generative adversarial network implementation from scratch with PyTorch. So stay tuned and do subscribe. Thank you very much for watching. See you in the next one.